Okay, so last lecture one of the things we accomplished was to rewrite Maxwell's equations in Gaussian units, and I am just rewriting the same. Hopefully there are no sign errors, and so the idea here is to ask what are the invariances of Maxwell's equations. Okay, so obvious invariances are as follows. We can see that if you look at, say, this particular equation, the left hand side of this equation is a scalar, so is the right hand side. Now this is a vector, so again each one of the three terms in this equation is a vector equation. Okay, so now you can see that since vectors are equal to vectors, etc., you can one says that the invariance under rotations is manifest. So instead of obvious, I mean, okay, so we should say the correct word is to say manifest, where you look at it and by inspection you see it. So it is invariant under rotations. It is also invariant under translations, and the easy way to see that is that there is no explicit dependence either on time or spatial coordinates. So it only remains that we need to check whether it is invariant under Galilean boosts to check if it is. So the Galilean group was done by taking all these various these two things plus Galilean boosts, but it turns out that this is not invariant under Galilean boosts. What I will do is to rewrite these equations in a manner where it will be invariant under something different, and we will see that Galilean boosts get replaced by what we will call Lorenz boosts. Okay, so so let me write out what was a Galilean boost. So let us say we had a boost in the x direction, then we would write something like x prime equal to x plus some velocity. So so let us write u t, then y prime would be untouched, z prime would be untouched, and t prime would be equal to t. This is what we meant by a Galilean boost, but a Lorenz boost is much more complicated, and I will write the form here, but we will derive it in a completely different manner. So what it does is it mixes x and t in a non trivial manner. Okay, and let us just write that out. So x prime one writes as gamma times x plus beta t. These two remain the same, but you get a change out here. So I have introduced a couple of things, gamma and beta. This is standard in courses in special theory of relativity. Beta is nothing but u by c, and gamma is square root or 1 by square root of 1 minus beta square. Okay, and c is the speed of light. So now you can so we can do something. If you think of c as a parameter, of course the world we live in, c is just a number, fixed number, but for this purpose we could think of c being formally being very very large, or u being very very small. So in other words, beta is very small. Dimensionally there is a problem here. This should be ct. Okay, so beta is taken to be very small. So when beta is small, so beta is much less than 1, gamma is approximately 1, plus corrections of course of order beta square for gamma, but we can see that what we see is that when beta is much less than 1 and gamma this thing, you see that you can actually recover these equations. Okay. So, Lorenz boosts turn out to be the invariance of this set of equations, and what we will do in the next 5-10 minutes is to rewrite these equations in a manner where this symmetry will be manifest. So, by inspection we looked at these equations and said they have to be invariant under rotations. We will do the same thing for these equations. Okay. So, but meanwhile it is useful to look at how these things are different. The key point here is that x and t can mix, this changes. Okay. Now, so let us go ahead, and there's just one nice comment to make. So, let us come back to this thing. Suppose we had a Galilean boost in the x direction and we followed it up with a Galilean boost in the y direction. If you compose the two of them, you get another Galilean boost. Okay, you use the vector law of addition, etc. It works here. But if you do the same thing, so we have a Lorenz boost in the x direction, you can follow it up with a Lorenz boost in the y direction. You can compose them, there is no problem, except that the resultant is no longer a Lorenz boost in a direction like this. Okay, and this has to do with the fact that Lorenz boosts do not commute, for instance. In other words, the order of the operations are important. Okay. So, I mean I have an example here of operations which do not commute. So, if I have a Rubik's cube, I could say rotate this by 180 degrees here, and if I followed it up with a rotation by 180 degrees on this thing, since there is a common edge, you will find that it matters what I do first or what I do later. But suppose I did this followed by this, there is no common, these things they commute. Okay. So, this is an example of operations which do not commute. So, we see these things even if you are solving puzzles, it matters, the ordering matters. So, it is kind of amazing that the generalization to this is not even obvious from looking at this. But like I mentioned towards the end of last lecture, it is important that we should be able to recover this starting from these equations in this kind of limit, because this is the limit in which we have actually studied Newton's equations. We never ever looked at situations where beta was close to 1. Okay. So, this is something which you have to sort of remember. So, now we just go ahead and revisit Maxwell's equations, and we will rewrite it. And first thing to notice is that I have written out two different, I have ordered it in maybe what you might consider a weird manner, because you might be thinking I should put del dot E and del cross E guys on the same thing, but the reason is that these two have sources and these two do not have sources. Okay. And so, we can go ahead and solve for these two equations, we can solve for them. So, we start with the obvious one, del dot B equal to 0. You can trivially satisfy this by saying that B is equal to del cross A. Okay. Now comes the interesting thing, we could go ahead and try to do a similar thing out here. We have already solved for B in terms of A, and this just follows. So, del dot B now becomes a trivial identity, and so we need to do this. So, let us look at del cross E plus 1 by C d by dt okay. So, now what you can see is that we can pull out a del cross. We could rewrite this whole thing as del cross E plus 1 by C into okay. So, this is now looking like what we did in electrostatics, where this term was not there, there was no A, when del cross E was equal to 0, we solved for it by saying E was gradient of some potential. Yes. Yes. Thank you. This is wrong. Thank you. Okay, so this is what you get. So we can solve for it now again. We can write E plus dA by d, this term which I will take to the left hand side, and the convention is to choose it to be minus gradient of the potential. So yeah, so the point here is we are going to assume that the functions are smooth. Okay, so we can exchange orders of derivatives. I mean, even here that is true, right? We assume that the x and the y derivatives commute. Okay, so now we can see that we have gone ahead and solved for E and B in terms of two other objects, the vector potential and this is called the scalar potential. Now we can go back and plug these two expressions into these equations. What I am going to do now is to do it for the first equation because it is less tedious, and as usual I will leave the next one as an exercise for you. Okay, so so what we have is del dot E is equal to 4 pi rho. So E is given by this, so let us just do this. So we can write this as del dot, okay, let me first write the gradient part. Yeah, so what is del dot del is a Laplacian, so we end up getting Laplacian square phi, and then again I will exchange the order of things because I am assuming that my functions are smooth. What I will do now to this is to add and subtract two pieces, and let me do that first. So let me use a different color so that you see what I am adding. Yeah, so plus 1 by C okay. Really I am doing nothing, I am adding 0, but I will combine these two and I will reorder things out here, and I can rewrite this combination. I will write this as box phi I will write some symbols out here, and then okay, I have to explain what these symbols are. Box is an operator which is called the D'Alembertian, which is basically so it is called the D'Alembertian, and this combination D dot A is nothing but 1 by C d phi by dt plus is this combination. So these are just definitions. So okay, Are there any questions? So, I will not disturb this bit, but I will erase this, and like the promised exercise will arrive now. The exercise is to show that the del cross B equation can be written as follows. Box A minus gradient okay. So, now the neat thing is that you can see that there is quite a bit of similarity between these two equations. All that is happening all that is happening is that phi here gets replaced by A, and of course, rho gets replaced by J out here. There are factors of C, etc. Okay. So, let us see how we can combine. What we will do now is to combine these equations. So, if you just do in raw counting, this is one scalar equation and there are 3 equations out here. We will write this as one equation with 4 components like we have done here, and so we will define a bunch of objects which we will call 4 vectors. So, the first 4 vector is x mu, it joins the space and time coordinate, and that is x 0, which we already defined last lecture. It was c times t, and the other one is just okay. It's important to note that I am writing this thing with an upper index. We will see later on in this course what the lower guy would be there. Okay. But at this point, all these guys have upper indices, or what they are called contravariant vectors, 4 vectors. So, then the next one, and this mu index runs from 0, 1, 2 and 3. So, 0 stands for the time coordinate, and 1, 2 and 3 are the spatial coordinates x, y and z. It is better to write them as this, and we will follow the notation convention that we will use symbols like I, j, k, the Roman ones for spatial indices, and the Greek ones mu, nu, etc. running over these. Okay. This will be a convention throughout this course, virtually no exceptions. So, now I define a 4 vector potential. We will see, you will see in a moment whether this is correct or wrong. We will see it. It cannot be d by dt because this is a vector, so I will require some operator. D by dt is not a vector operator. Okay, that is an easy way to check, but you can go back and verify this. Okay. So, A upper mu is this guy, and we will also define a 4 current. So, this is a 4 vector potential, but on and off I will use the term vector potential, and in context you have to understand whether I mean really this vector potential or whether I mean this, and there will not be an ambiguity, you will see. And j mu is 0. So, you see something very nice happening. All these 4 vectors are made up of one element, the first 0th element, which is a scalar under rotations, and the next element is a normal vector under rotations. Okay. That is true for every one of these. Okay. Now, you can see that I should be able to combine these equations in the following way. So when mu equal to 0, a 0 is phi, so you end up getting this particular equation, and the rules are as always, we have a one upper row and a lower row, they have to be summed over, but now they are summed over 0, 1, 2 and 3. Okay. And so I need to still define for you what these operators are. D rho is a very natural operator, it is just definition. Or equivalently, if you write it out, you can see d0 is defined to be d by 1 by c d by dt, and di is the usual d by d xi. But the upper mu has a sign problem, it is not a problem, but it has a sign difference, and in our notation it will go like 1 by c. So, we will just write this as d0 and minus del. Okay. So, there is a sign issue which comes about. So, the upper guy, so this is a first instance you see that these two actually differ, okay, and in this case it is only a minus sign. So, now comes the rule, I will give you a working rule, is whenever some index is summed over, you end up getting an object which is scalar, not just under rotations, but also under Lorenz boosts. We will formalize this whole thing in the rest of the lecture, but right now, so this guy is a scalar. This operator box also has can be written in a nice way, and then it shows that I require this, can be written as d rho, one upper and one lower, because the rule is that I cannot sum up two lower or two upper. Okay, right now it is just a rule, but there is a lot of meat on that in that thing. It is useful to remember the rules. So this is a scalar, this is also a scalar, but this object is a vector. So roughly again it is like before, it is a scalar under Lorenz boosts as well. So this is a 4 vector, this is also a 4 vector, and this is also a 4 vector. Okay. So we have an equation which involves 4 vectors, and I am just going to at this point claim that 4 vectors transform nicely under Lorenz boosts and rotations, of course, that is easy, that is manifest already, so that we need not worry. So I just need to discuss how they transform under Lorenz boosts. Okay. So but that is already done for you, I will explain to you how. X mu, I wrote out in this board where I just erased something, I had written out how under a Lorenz boost x mu transformed. We saw that if it was a boost in the x direction, the x and the t components mixed. Okay. So now the statement is that all 4 vectors by definition transform exactly like x mu under Lorenz boost. So wherever you saw x0, if you want to work out the transformation of this, you put a0, wherever you saw the spatial x, you replace it with a. That is the rule. So I have given you how it transforms. The important thing is they are all linear transformations. By that I mean you can write x mu prime equal to some matrix times x mu. Think of them as column vectors. So I organize it as x0, x1, x2, x3, there will be some matrix. Exercise for you, write out that matrix, it is a simple matrix. So you can see that it is just a linear transformation. So this equation gets transformed under Lorenz boost to some linear combinations of itself, that is all it says. Okay. And I still have to tell you how a lower index transforms, but I claim that even that is obvious if I say, if you use the fact that I want this guy to be a Lorenz scalar. So if this transforms by some matrix, an upper guy, the lower guy should transform with the inverse. Okay. So what we have achieved here is to show that Maxwell's equations are invariant under Lorenz boosts, not Galilean boosts. So now we need to actually understand what we mean by all these various things, but before that let me define for you the Lorenz group. Okay, this is the group given by rotations and Lorenz boosts. Okay. So, it is important. So, this statement is that the fact that it forms a group is it is important that a combination, like I said, two Lorenz boosts, if I compose them together I do not get another Lorenz boost, but what you get is a combination, a complicated messy combination of a rotation and a Lorenz boost, another Lorenz boost. Okay. We will prove all these things in a very nice manner, but at this point this is so rotations had three parameters like the Euler angles, and Lorenz boosts we have again 3 independent x, y and z. So, we have 6 of them, and then you can also, if you, there is something called the Poincaré group. You add translations in space time. I no longer will say space and time, because now we have merged them all. So, we just use a single word, we call it space time. So, this has 4. So, in some sense the Poincaré group plays the role of the Galilean group in non-relativistic setting. And okay. So, what we will do now is to understand how to go ahead and define vectors. What do we mean by vector under some group or whatever it is. Okay. So, we start with, we go back to actually normal, I mean even here I said under normal rotations there is a vector. What do we mean by this? What is a tensor? What are all these things? Are there generalizations of that, and how general can we get? Okay. So, let us just one small bit which I just forgot is that we made a change of variables. We went from E and B, we went to A to phi and A by solving the equations, but this is actually not unique. Okay. The phi and A are not unique. You can get, so I would ask you to play with it and see what is the freedom that you have, and okay. So it is not the point here is phi and A are not unique, but it does not matter which, there are inequivalent phi and A's, rather equivalent phi and A's which will give the same E and B, because those are the physical observables. Okay. Another important point is Euler-Lagrange equation is always second order, but these equations are not second order in anything, they are first order equations. And so in some sense you can see that the right object in for Maxwell's equations are actually A's. A is the 4 vectors, because you end up with second derivatives, which is what you normally see in classical mechanics. Okay. And the most amazing thing is that there exists an action which gives you these equations of motion. This is again something which we will see. Okay. So we will go back and revisit what we mean by a vector. Okay. So the point here is that we were very happy when we saw, I mean I said that things were manifestly invariant when we wrote things in terms of vectors. The reason is the following, is that first thing is, yeah, so let us so first point is that it is just something which has 3, let us write it as a column vector, or we could write it as, so it is an entity which we will call a 3 tuple. Okay. And it has certain properties under rotations. So how? Okay. And the answer to that is very easy. It transforms exactly like the coordinates, like displacements to be precise. So, by that what do we mean? Suppose we have a rotation. So, let us write this way, R x prime of R I is some matrix x j. So, this is, let us say, the coordinates transform in this fashion. So, we are going from coordinates x prime, y prime, z prime to x, y and z, which I write as x 1, x 2, x 3 as here. So, the statement is that any vector, we will call any object a vector, or better, all vectors as exactly like this, except you write some arbitrary vector. So, let us ask what are the properties of this matrix, what characterizes these things. We know that under rotations the length of a vector is preserved. Okay, so, the property of a rotation, very important actually. Lengths. So, if you give me a vector, how do you define its length? The normal definition of any vector is just the sum of all its components. But let us write it in index notation. You would write something like this as where delta I j is the Kronecker delta, and this I index is summed over because it is one upper one lower repeated, same story out here. This is called the Kronecker delta. However, if you try to write this, if you think of V as a column vector, then this term has to be written in the following way. V of I by a column vector. This is just a convention which I will follow usually, like I did there. Then you will see that we can rewrite this whole process, this norm, as the transpose of this, which is a row vector, and the Kronecker delta is the identity matrix. Okay. Then you can see that if you carry out this thing, obviously you recover this thing. So, there is a little bit of work we have to do to understand how this happens, and this has to do with how matrices are multiplied. If two matrices are multiplied, so let us just take two matrices M and N. So, let us say they are 3 by 3 matrices. So, M1 1, M1 2, M1 3, so on and so forth, multiplying matrix which is N1, N2 1, N2, N3 1, so on and so forth. We could write more terms, but for me I just need to multiply out the first row and the first column. So, let us just concentrate on this. You end up getting M1 1 N1 1 plus M12 N21 plus M13 N31. The rest of the terms are not so important. Let us focus on this. What you can see here is that the column index of the first matrix is summed with the row index of this thing. Okay. So now coming back to here, let us look at delta ij. The first index is the row index and this is the column index. So this column index is going with the row index, this is like so it works out correct. But out here you see that this is the row index and this is a column index, so it does not work correctly, and so you need to do the so the transposition is exactly the operation which takes care of that. It converts a row index into a column index. So this is some it takes some practice to get used to going from this form to this kind of a form. Okay. So but this so it is very important to realize that when you write something as a matrix, you have to ordering matters. So now we can also go ahead and ask how this looks, and this is nothing but, so we could write that equation. So let us call this equation star again, star. So star can be written again as simple matrix multiplication. So it is just R1 1 R1 2 R1 3, and look at the indentation, tells you which is the row and which is the column. Okay. Or in short we can hide all these indices and write V prime equal to the matrix R multiplying V. It is the same thing. Okay. So now this so now we can characterize rotations. We were told that rotations actually preserve the norm, and let us understand how that works. So we have to ask what is V prime square. Okay. Since this is just the identity vector, so this just gives you V transpose. So let us see what we get. What we get is this is equal to V prime transpose dot V prime, but what is V prime? It is R dot V. So we end up getting under transposition the order changes. So we end up getting this is equal to V dot and rotations preserves the length. So this should be equal to, and this has to hold for all vectors, not one particular vector, for any vector. For any vector this has to hold, and that can happen only when R transpose R equal to identity. Yes. Okay. So now we get a sort of independent characterization of what we mean by a rotation matrix. It has to be some matrix which preserves the length, but that turns out to be this statement, that it is a set of matrices which satisfy this condition. Okay. This condition is called the orthogonality condition. Does anybody know why it is called the orthogonality condition?
If the first three set of unit vectors are orthogonal, and the final three sets are also orthogonal.
Yeah. So if you choose a basis for these vectors, you choose an actually orthonormal basis, what you will find is that it will map, it is a set of transformations, linear transformations which map orthonormal vectors to orthonormal vectors. Okay. So, that is why it is called the orthogonality condition. Okay. So, this is the characterization of rotation matrices. There is a little bit more structure in this thing which we will discuss, but before that there is one simple generalization. Here we just said that it is a sum of 3 components, but in principle I could have replaced this with adding many more components, and let us do that generalization. Up to some d. Okay. Now, what I will write as a 3 tuple will become a d tuple. It is a vector with d components, but most of the things which I said will go through. The only thing in, and this form nothing will change except I and j, instead of running from 1 2 to 3, they will go to 1 to d, and R will now become a d by d matrix instead of a 3 by 3 matrix, but it preserves the same property, it preserves the length of a vector. Okay. So, we can already see a very nice generalization, and so we will do that right away. We will, for the rest of this lecture, we will assume that this is a d by d matrix which satisfies this condition. So, we will now use we will give a definition. A d by d matrix R is called orthogonal if okay. So, that is just what I have done is what is called abstract away the what was our normal definition. We have just gone from that and we have come to something more general. Okay. What are its properties? Okay. The first property is that if R1 and R2 are orthogonal matrices, then R1 dot 2 as well as R2 dot R1 are also orthogonal. This is extending whatever we know. If you follow 2 rotations by another rotation, the combination will give you another rotation. Okay. Second bit is identity. R equal to identity is an orthogonal matrix. The third property is that if R is orthogonal, so is R inverse. That is not hard to see. If R transpose equal to 1, it implies that R inverse is R transpose, and for finite matrices the ordering the left the inverses are the same. Okay. So, this also implies R dot R transpose as well. Okay. And of course, the last bit is associativity. That means, if you have 3 matrices R1, R2, R3, the ordering does not matter, okay, and you will get another rotation matrix. Okay. So, this defines for you actually a group. Okay. These properties we will these 4 properties determine a group which is called the orthogonal group, and the symbol for that is capital O and in brackets d. Okay, important that it is capital letters, because the lower case means something else. Okay. Let us look at this thing and let us take a determinant of this. What is determinant of R transpose? If you use this fact that it is orthogonal, it is equal to 1. But what is the determinant of product of two matrices? It is a product of the determinants. So, this but any matrix and its transpose have the same determinant. So, this implies that determinant of R equal to square equal to 1. Okay. Or determinant of R is equal to plus 1 or minus 1. Okay. There is one more definition, that is, we will call a matrix, rather an orthogonal matrix is called special if its determinant, orthogonal matrix R is this. Okay. The reason of looking at plus 1 not minus 1 is that if you restrict yourself to the subset of orthogonal matrices with determinant R equal to 1, under composition it closes. If you restricted yourself to saying I look at the subset of orthogonal matrices which have determinant minus 1, you take any two guys from that thing and compose them, you will end up getting a one with plus 1. So, you get everything. So, this is, so that is why you choose plus 1, okay, and that gives you closure. The rest of it is the same story. So, you get something called, so special orthogonal matrices form a group SOB. Okay. And so, usually in 3 dimensions. So, when d equal to 3, by rotations rotation matrices, one means one puts in the one means that we are considering SO3 matrices, not O3 matrices. Okay. But of course, you are interested in objects how they transform under O3. So, you need to consider examples of matrices which are orthogonal, but with determinant minus 1. Can you give me some examples, anybody from here, of some simple transformation that you know? Parity. So, goes to minus okay, but this is true only in odd number of dimensions. If it were in even dimensions, suppose you are in 2 dimensions, if x1 x2 goes to minus x1 minus x2, that has determinant plus 1. So, that is not a determinant minus 1 matrix. Okay. So, parity is not defined in 2 dimensions by, you should remember this important point, that parity is not defined by just reversing the sign of all coordinates. This is a very common mistake among people. Okay. So, but in 3 dimensions you could do this, but simpler is to just choose a mirror reflection. Okay. Say one of them x1 goes to minus x1, all the other coordinates are invariant, say. So, that would be an example of this thing. Okay. So, I will stop here, we will continue from here, we will understand what we will go back and revisit what we mean by vectors, and we will add in the fact that there are orthogonal transformations which are not special orthogonal. It puts extra flavor onto what you mean by vectors. There are polar vectors, there are axial vectors, and so on and so forth. So, that is what we will do. We will also give the formal definition of a group, which will basically be these things, and we will move on to giving examples.